There, now there's sound. Oops. All right, so the only thing that wait does check for is if the child process I waited on was equal to the one I spawned, so if someone tried to quit the shell, all it does is restart it. So it creates a new child process and then turns that into the shell. Otherwise, it checks for errors, and otherwise, if it's an orphan, just does nothing and then goes back into the wait. So you can see that this does its two jobs. It launches every other process, which is just SH, and then it just waits over and over and over again. So this is a implementation of init, courtesy of MIT. So with that fun detour out of the way, we can talk about old operating systems, like just because they're historical things, I guess. So back in the day, when you only had a single CPU core and it wasn't very powerful, operating systems did something called uniprogramming, which just meant you can only run one process at a time. So you can't have two processes running in parallel or concurrent, no matter what. It's just a really dumb operating system. You just tell the process you want to run, it runs it until it's done, and then whenever it's done, then you can run another process. And that's all you can do with it. So if you've ever heard of DOS before, that's what DOS does. It can only run one thing at a time. So anything nowadays is multi-programming that allows multiple processes. So two processes can then run concurrently or in parallel, which if you know English, that sounds like they're the same term. Once we get into threads, we will figure out that to computer scientists, those terms actually mean something different. So, but the goal here is just to say that two modern operating systems, they just try and run everything in parallel and concurrently as fast as humanly possible, and otherwise try and get out of your way. So if we talk about the mechanics of actually switching a process, the scheduler is the thing that decides what processes to run at any given time, which we will talk about in the next lectures. But we know to create a process, the operating system has to at least load it into memory. And then when it's waiting or in that ready state, that's when the scheduler that we'll see later decides if it should run or not. But first, before we get into that, we can first describe the mechanics of switching processes. So to see where it fits, well, this is the core scheduling loop that negates a decision. So whenever it makes a decision, it will pause the current running process, save its state so you can restore it later, which would be all those virtual registers. So it would save all the registers to memory on a stack is probably the easiest thing to do. So you can actually see this code in that kernel. That's what it does. Then from the scheduler, it will get the next process to run. Then after that, it will load its process state and let it run. So it would do the opposite of saving its state. So if you just pushed a bunch of register values into memory, well then to load it, you have to pop them from memory in the opposite order, and then you would restore all of the registers for that process, and then you can just let it have the CPU and start executing. So when it comes to actually stopping a process and making that decision, we have two options. So the first is something called cooperative multitasking. And that means the processes will tell the kernel or the operating system that it can pause it. So it would be like, okay, you can pause me now if you want to run something else. It's completely opt-in. And if a program just wants to use the CPU, it could just never call that until it exits, and it would get the CPU and never relinquish it. The other option is what's actually used, called true multitasking, and the kernel or operating system would retain control and pause processes. So in order to maintain control, the operating system can either give a process a certain time slice, and then after its allotted time has passed, well then it goes ahead, takes over, and then decides to switch to a different process if it wants to. The other way to implement this is the kernel can wake up periodically using interrupts and then do the scheduling in that interrupt handler and then switch the processes from there. So on CPUs, there is timer interrupts you can program. So you can just program it. The kernel, before it launches it, could program in, hey, wake me up in 10 milliseconds, and then start executing that program. Then the kernel would get a timer interrupt, and it can go ahead and switch to a different process. Was a yawn? Okay, good. All right. So that process of saving all the state and then loading another state, that process of swapping processes, wow, that's a lot of processes, is called context switching. So at minimum, we have to save the current registers. We have to save all the values using the same CPU we're trying to save on, so that's why they have to go into memory. So on some hardware, there is a lot of registers. So like on x86, there are special registers for floating point, vector instructions. There are so many registers on your CPU that saving that state can actually be pretty slow. And if you just have to push for every single register you have, that could take a long time. So there's going to be some hardware support for saving sets of registers at a time. And then you also use that with software because, hey, if a program doesn't use floating point registers, there's no point in saving them and wasting that memory and wasting that time to save them. So context switching is like pure overhead. And what does overhead mean? Overhead just means it's work we're doing that is not productive. So the mechanics of switching processes and saving their state, the goal of your operating system is to run processes, not to switch processes. You want switching to be as fast as possible, and you want that time to be as negligible as possible. And otherwise, you want 99% of the time, your kernel should be running processes, not saving. So you want that to be as fast as possible. So that's why we'd want to do things where, like, if a process doesn't use floating point registers, we don't bother saving them, because otherwise we're just wasting time that we would rather have for other things. All right, now we can talk about a new IPC call. So yeah, and before this, so I graded lab 1 and 2, or 0 and 1. I forgot to press a button on Quarkus, so I'll try and do that after. But spoiler alert, most people got 100, so it was probably easy. Lab 2, gonna be harder. So lab 2 will not be impossible, but it's process management, and you won't have to directly use pipes, but after this lecture, you should be able to do it. And in fact, in lab 2, your process manager, there's like a 20% part that you don't have to do, but if you do, for 20%, you can become a sub-reaper, which is fun. So that's the like extra thing for lab 2. So let's talk about some new IPC. So I showed you before that there's like this bar character that represented a pipe. Well, it actually corresponds to a system call. So there's a pipe system call that takes as an argument an array of 2 integers, and it returns -1 on failure, sets error no, all that fun stuff. Otherwise, it returns 0 on success, and then writes values to that array. And it will write 2 values for that array, representing 2 file descriptors for a one-way communication channel. So it would create a file descriptor for the read end of the pipe. So for this file descriptor, you're allowed to read data from it. And from this file descriptor, you're allowed to write data to it. And the rule is, whatever you write to the right end of the pipe, you can read from the read end of the pipe. And the way to think of it is, well, it represents a buffer, like just some space that the kernel manages for you, so you can pass information between processes using reading and write. So you can think of it as just a kernel managed buffer. Any data is that you write to it is you can read it from the other end of the pipe. And this we'll find out is useful through an example. But first, before you get into the example, which is where we'll spend most of the day in questions, so there is an ampersand you can use in your shell as well, which basically takes this process and then runs it in the background and returns immediately. So it would do the same fork thing, but it would return. So if you did something like sleep1 ampersand, it would start a sleep process, and then it would just let it go. It would get reparented, and then whenever it's done, it would go ahead and return, and then on your shell, you would see the process ID whenever it's done. There's another one. So we saw the pipe character that created pipes between two processes that we'll get into more today, but that while true fork, this is the sneaky bash version of it. So this defines a function called colon that takes no arguments, that calls colon with a pipe to colon. So they feed data to each other. This is just a way that you can launch two processes. And then it does an ampersand to shove that off into a background. And then here it finishes the definition and then calls colon to call it again. So this would create two colons, throw them in the background every single time. So this will do that exponential fork bomb explosion we saw before when we had while true equals fork. But this is like the sneaky bash version of it. Don't run the command. Only give this to like other undergrads that don't know what they're doing or something like that. But you know not to run that. All right, let's see our example. So I imagine we'll have a lot of questions, and that is good. So what are we going to do? So first, in this program, I will have a main. We can start arguing about what it does by reading main. So main will declare an integer array of 2 elements, and we will call it FDs, and then we will call pipe with my check function. What does my check function do? Well, it just saves me from checking a -1 over and over again. So it will check if the return value from the argument is -1. If it's not -1, it just returns because there's no error. Otherwise, it will have that same error handling code we all know and love. So that's just a shorthand just so I check for errors. So here, I do a pipe system call, and if it's successful, it will create 2 file descriptors. So I already know file descriptor 0, 1, and 2 are already open. So it would probably open file descriptor 3. That would be the same as FD's 0, which would be the read end of the pipe. And then knowing that they go up sequentially, 4 would probably be file FD's 1, which would be the right end of the pipe. So then after that, I do a fork. At the time of the fork, the 2 processes are exactly the same. So the parent and the child process will have the same file descriptors open. So they'll both have file descriptors 0, 1, 2, 3, and 4 open in both processes. And file descriptors, you can think of like pointers managed by the kernel. So they'll be exact copies, and what their file descriptors point to are going to be the same thing, but the file descriptors themselves are independent in each process. So both processes will have all those file descriptors open, and the only difference is going to be the return value from fork, which we immediately check. So in the parent, we create a string called howdy child. We get the length by calling string length on it, and then we do a write system call to the right end of the pipe. And we give it that string and how many bytes to write. And then after that, all we do is check if there's any error. And then in the parent, it just closes our file descriptors and then terminates, and that's it. In the child, we declare a buffer of that magical size, and then we immediately called read from the read end of the pipe up to however many characters we have, check for errors, and then we would print off any information we read. So if I go ahead and run this, I see the child read, howdy child. Any questions about that? This is, yep.
Do you have to instantiate the pipe anywhere, or did I miss that?
Yeah, so the question is, do I have to instantiate the pipe anywhere? So it's just the pipe system call sets the file descriptors for you. So yeah, after this pipe system call, If it's successful, it would set FDs at index 1 and FDs at index 0 and index 1. Yep.
What if the child reads before the parent writes 100%?
Yeah, so that's a good question. So what happens if the child reads before the parent writes? So because we have this fork, it could happen in any order. So after the fork, the child could actually start executing first. In that case, we would go into this else statement, declare a buffer, and then call read. And read's a blocking system call. So right now, no process has written any information to the pipe. So it would just sit and read and then wait for someone to call write on it. So if it runs first, it would just sit there, wait for someone else to call write. So that way, the child process will get put to sleep on read, and then eventually the parent process will run and then call write, and then the kernel will know that, hey, this one's waiting on some data, I'll give it some data. Any other questions on this one? Yep.
Just like, I don't know if you remember this already, but let's say we do that situation where the child reads first. The only way that the parent can write to it is if it has like a separate CPU, right? Like unless, like if they're running on the same CPU, then they just won't from it.
Yeah, well, the question is, if the child goes first, would the parent have to be in a different CPU? Yeah, so the answer to that is, well, the child could run first. It would get into this read, which is a system call. Then it would go into the kernel. And then the kernel knows it's waiting for something. So even on a single CPU, the kernel can be like, OK, that process can no longer run anymore. The scheduler would be like, OK, what can I run? And the answer would be the parent. So then it would load the parent state and then start executing the parent because it's waiting on it. So yeah, you do not need 2 CPUs to do this. So eventually it would wake up, yep.
What if the parent doesn't write at all?
Yeah, that's a good question. What if the parent doesn't write at all? So this is a question we can actually answer now. So what happens if I do something like that? Anyone want to give me their full explanation for full points? Yep.
I'm just guessing, maybe there's like a timer for the read function, like different ways to.
So you think that, so the child would, let's say the child goes first, it gets in the read, and it's sitting there waiting for something, and then the parent executes, doesn't do anything, closes, so the child's just kind of chilling, and eventually read would time out, it would get an error or something like that. The answer to that is no. So read will block until it gets data. So in this case, there's no timeout or anything with it. So if there's no timeout, what would happen to it? So it would still be alive on that read, right? What happens to its parent? Huh? Yeah, it's an orphan, right? So the child process would be an orphan. And it would just be an orphan, right? It would get reparented to something, but it's still doing read. So it's just an orphan that's just waiting for stuff. So in fact, let's make sure that that's actually true. So that is a warning I don't need. So if I run it now, like you said, it should be an orphan, right? So I run it, it returns immediately, so that means the parent's done. So if I want to check if a process of that name is still running, what do we remember what I should type? Anyone? Yeah. PS, yeah, I want to get its process ID though, because I'm lazy. So if I just do PID of pipes, that will go through that proc directory. You could write this now, right? It just goes through the process directory, finds something with a matching name, and then tells you its process ID. So it's still running, and I could, in fact, go look at it. See, hey, it's still running, it's sleeping, its parent process ID is 1, so it got reparented, so you are correct, it was an orphan, and it's just going to sit here forever. So it's obviously not going to do anything useful. How do I get rid of it? Yeah. Kill -9. Do I have to choose violence? Can I just what happens if I just do a normal kill? Normal kills should be fine in this case, right? I didn't write a signal handler that ignores it or anything, it'll just exit. So I don't have to choose violence today, but I could if I wanted to. And then if I check, hey, it's not running anymore. So full marks, orphan process. All right, any other questions? Yep.
Could a bad actor create a large number of, I guess, child processes that are forever reading to try and clog up your OS?
Yeah, the question is, could a bad actor just run a bunch of these programs and clog up your own OS? And the answer to that is, you don't even have to be a bad actor, you just have to be a bad programmer. So this will just clog up, it'll just create a process, and it'll essentially be like a zombie process, but worse, because it's actually could execute. So it's actually maintaining a bunch of other state, it's maintaining memory, and yeah, so you could clog up a system by doing that. In fact, this is why you are using your own virtual machine, because if you clog up a system, it's your system. And if you want to fix it, you just reboot it. And you reboot a virtual machine, which is a lot less annoying than rebooting your actual machine. All right, so another thing to know about this is, here, I will do something tricky to illustrate another. So remember that file descriptors are kind of like mallocking and stuff, where if you open them, you should probably close them. So in this case, in the parent, I will go ahead and close them, and then in the child, well, if I look at this code, the child never uses the right end of the pipe, right? Never uses the right end of the pipe. It just reads from the read end of the pipe. So if I want to be a good programmer, I should close it immediately when I know I'm done with it. So in this case, I know I'm done with it if I'm the child, and I should close it immediately. And otherwise, I'll do the read from it and then close it when I'm done with that. So in this case, if I compile this and run it, oops, Bill. I get some output from the child. And if I look at it, it's not running. I didn't create an orphan. Anyone want to guess what's happening there? Yep.
File descriptor with zeros, or yeah, first file descriptor is closed. So when it tries to read from it.
So this is the right end of the pipe that I close. Okay, you?
I was gonna say something similar, like you just like close one of the pipes like twice, like that causes like an exit status.
Yeah, there's a guess I closed one of the pipes and that caused an exit status. So if I look at it from this one, this didn't have an exit status at all. I didn't create an orphan, but I saw this message. So if I saw this message, what does that mean about the read call? Did it finish? And it finished, and I don't see any information, so it probably returned 0 bytes read. What does 0 bytes read from read mean? Yeah.
It means either read failed or there's no file to read from.
So -1 means there's an error, and 0 means that no, it's not possible to get any output from it. If this was a file, it would mean end of file. So in this case, what 0 means for pipes, the kernel is actually very smart about pipes. So what 0 means if you are reading from a pipe means you have read everything you can possibly read from that pipe, and it is not possible to write anything more to that pipe. So the kernel will keep track of how many processes have a file descriptor that refer to the right end of the pipe. If there are bytes read, because it's not possible for that pipe to get any more data anymore. So that would return, it would print that, and then just close the file descriptor. So, and that's only possible because we closed the right end here, right? Whenever I moved that to the end, it was technically possible because the process that was waiting on the pipe had a reference to the right end of the pipe still open and could technically still write to it even though it is in a read system call. How would that be possible? So the main program would be in the read. What happens if I send this process a signal? Could it start executing something else? It could. So if I send this process a signal, it is theoretically possible it could start running some other code, and then it is also theoretically possible that process could write to the right end of the pipe and generate some more data. Unlikely, yeah. Technically possible, yeah, it's technically possible, so the kernel needs to be conservative, which is why we created an orphan process before. There was still a right end of the pipe open, so read couldn't return. All right, any questions about that fun one? Okay, let's go to a more exam-y type question then. So, we know all about forks now. In fact, we could have reasoned about this in lecture 4, but these are fun exam type questions. So for each program shown below, state whether it will produce the same output each time or whether it may produce different outputs each time when run multiple times, and explain why it behaves like this. So explaining why it behaves like this is like, why is that freaking out? Is like, how many processes does it make, and what do they print out? So let's go ahead and read that code, and let me know your response. All right, any initial guesses by just looking at this? Yep.
I'm going to say it produces different output when run multiple times. What does that mean?
So if I run this program, will I get, each time I run it, will I see something different?
Call it and execute it multiple times?
Yeah, so if I execute it and then execute it again, am I going to be guaranteed to get the same output?
Same order.
Same output, same order, same thing. So here, yeah, no, but what am I going to see here? Do you know the output I'm going to see?
I think it's going to be somewhere along the lines of descending 4, 3, 2, 1, depending on the order in which your forks actually execute and making child processes.
Yeah, 4, 3, 2, 1. Yeah, it's,
It's like 1, 4, 2, 3, 4, 4, something like that.
4, 4,
Sorry, 4 twos and then like 8.
4 twos. So we're going to have like 16 processes here? Something like that? All right, well, let's just go through it. So, everything starts at main. So, I will just, a process has to run main. Let's just make it up. I like saying process 100. So, process 100 starts executing main, creates a variable called I. What is its value? 4, right? Nothing tricky so far. All right, is I equal to 0? No, so we will go into this loop. So then we call fork. What will fork do? Yeah? Yeah, create a new process and it will be a child. So here I will put up the parent-child relationships up here. So 100 created 101. So I will be super creative with my names. So process 100 created 101. If it is an exact copy, does it have an I? Yes. What is the value of I? Okay. How do I? So now, which of these processes are going to run? Child. Anyone think the parent? Parent. In this point, you don't know, right? 2 processes, your kernel decides. So you have to, right now we have no idea. So let's just say 100 runs for some reason. So in process 100, what did it return from fork? 101, right? So it got the process ID of, fork returns the process ID of its child. So it would have returned 101, then created PID, and then assigned 101 to it. So now it could go check this if statement. So is PID equal to 0? Sorry. No. So what's it going to do? It would print off I. What would it print? It would print 4, and then exit 0. It is now dead. So it would print 4. Now I have no other choice. There's only one other process to run. It's 101. So what would it do? Well, it would return from fork. It gets PID equal to what? 0, right? It is the child. So it gets the process ID equal to 0. Then it would check here. Is process ID equal to 0? Yes, it is. So it's going to do I minus minus. So its I is now no longer 4. Whatever. It is now 3, right? Then it's going to make it to the end of the while loop. And then this PID variable goes out of scope. And it goes back up to here. So now in that process, is I equal to 0? No. So it would do the same thing. It would fork again. What's it going to create? 102. See, we do not have to be imaginative with our child names. So unlike real life, we can be engineers and name things and everything's fine. So 101 created 102. So in 102, does it have an I? Yeah, what's its value of I? 3. Why? Why is it 3, not 4? Yeah. Yeah, it copied the parent at the time of the fork. Whenever process 101 called fork, I was equal to 3. So in the new one, I is equal to 3. So now at this point, we don't know which of these processes will run first. Let's, for fun, just say 102 runs first. So 102, what would it return from fork? 0, right? So it creates PID. It's equal to 0. And then it would check this if statement. Is PID equal to 0? Yes, it is. So it would do I minus minus. So its I goes from 3 to 2. So should I do this? In the other one, does it go from 3 to 2 as well? No? Why? Yeah, they're separate processes, right? So one doesn't affect the other. So in 101, I is still equal to 3. So process 102 would change I to 2, and then PID would go out of scope, and then it would go back up to this loop. Is I equal to 0? No. So it would fork again. It would create probably process 103. Wow, that's a big arrow. So in process 103, does it have an I? Yes. What's its value of I? 2. Okay. Which process between those 3 runs? Thumbs up? Yes. Yeah. Any one. There's no specified order here. So which one do we like? 103. We like 103? All right. So 103, what does it return from fork? 0. So its PID is equal to 0. It would go ahead, fall into here, I minus minus. So it would have to change I from 2 to 1. Then it goes back up to the top of the loop. PID goes out of scope. So now, is I equal to 0? Not quite. So it would go in and then fork again. What does fork do? Oh, we're creating process 105 or 104. So in 104, does it have an I? Yeah. What's its value of I? 1. All right. What executes next? Yes again, don't know. Let's say process 104 goes. What does 104 return from fork? 0. So then it would check here. Whoops. So it would check, is PID equal to 0? In this case it is. So it would subtract 1 from I. So I is now 0. So it would fall out of the loop. PID would get out of scope. And then we would check this statement here. So does I equal 0? Yeah, I equals 0 now. So it wouldn't go into the body of this while loop. It would go to the end. And at the end, it returns 0. So it just kind of dies, right? It just exits. Doesn't print anything. It's just exits. So in the rest of the processes, well, let's pick 102. What does 102 return from fork? Yeah, 103. Because that was the child it created. So it would return 103, then it would go into this else statement, and then it would go ahead and print 2, which is the current value of I, and then exit. 101, well, its fork would return 102, so PID would equal 102. It goes ahead, it would print out 3, and then exit. And then sooner or later, 103 would execute. Its PID would be equal to 104 from its return value of fork. It would eventually print 1 and then exit. So without counting the original child process, we create a total of 4 processes. So you wouldn't count process 100 because that's what started executing main. But through that, we created process 101, 102, 103, and 104. And each of them, except for 104, printed a number, and they were all different. So we'll see 1, 3, 2, and 1. This time, when we argued about it, the order we saw was actually 4, 2, 3, 1. Is that the only order I have? No. What else is possible? Yep. Yeah, any permutation of them. There's nothing to stop it from being in any order whatsoever. Okay, great. Same as the previous question, except we just added this line. So we just add weight PID. Yep.
What does weight PID do?
So weight PID, it's the same as wait. So wait for a child process to finish or terminate. Yep.
That just print back from like 0, 1, 2, 3, 4. Because all the very first one was.
Yeah, you just think it's just 1, 2, 3, 4 all the time? Yeah, same thing?
Yeah, I think so.
Yeah, 1, 2, 3, 4 all the time, right? So why is that? Well, if we get back here, the reason that 100 could print 4 immediately, like it could just start executing 4, or sorry, it could just start executing, and then we got into this else branch, and then it printed, and then exited. But if we have a wait PID here, it did wait on PID. So in this case, 100 before it prints anything would wait for process 101 to finish. So even if it ran first, it would get to that point and then it would be waiting on process 101. So it wouldn't print anything until 101 is done. Then 101 would, before the print, would do the same thing. It needs to wait on 102. Then 102 needs to wait on 103. Then 103 needs to wait on 104. Then 104 needs to wait on 105. 103 needs to wait on 104. And then 104 eventually just dies without doing print at all, right? So as soon as 104 finishes, then the wait from 103 finishes, and it would print 1. And then only after that process finishes, so it would print 1 and then exit. Then after that process is done, 103 would be done. So in 102, wait would succeed. And then this process would print 2. Then same thing, then we would get 3, then 4, and then it would always be in that order because of the wait. Cool? All right, cool. Yeah, that's it. So just remember, pulling for you. We're all in this together.